Okay, so good afternoon, ladies and gentlemen. Welcome to the monsoon seminar this week. So our speaker this week is Ray Zammit. He is from Malta. Ray is a geologist and a paleoceanographer. He did his PhD at the University of Cardiff in the School of Earth and Environmental Sciences, and was a visiting lecturer at the University of Malta. So he finished his PhD in February this year, and prior to that he did a bachelor's degree and a master's degree at the Open University, also in the UK, and he's generally interested in paleoclimate evolution and the development of environment in the Mediterranean region, especially during the Miocene. So without further delay, I'm going to hand over to Ray. As usual, if you have questions, please put them into the chat and I'll call on you at the end. And if you could mute yourself, that would be great. So Ray, please take it away and share your screen. Thank you.
Hello, good afternoon to people in Europe, and good evening and good morning to people following from the other continents. Thank you for that introduction. So I will be talking about the Miocene in the Central Mediterranean. I will be exclusively discussing samples from Malta. So from my home island of Malta. So here I just chose as my background, this is the Russell Pellegrin section in Malta, which hosts the GSSP for the Langin-Serevalian, which is hosting the mid-Miocene climate transition. So that is one of the sections I will be talking about. So before I get going, I just would like to list the people to some extent or others have been involved in my research at this moment. Most of what I will be talking about is research that has come out from my PhD studies, which I have completed past February. So I'd like to start a bit with looking at the background climate of the Cenozoic. So we know there is this gradual change from a warm house world to an ice house world, and I will be focusing in particular on this section here, which is in the Miocene. In particular, we look at two ice sheet expansion events in Antarctica. So one of these is right at the beginning of the Miocene. The other is in the middle Miocene. So what I will be discussing happened sort of between these two ice sheet expansion events. Now, apart from the general increase of the Antarctic ice, and at these 2 points, we know that somewhere around the Miocene, we have the closure of the Mesopotamian Seaway. I know that a couple of weeks ago, Bialik was here and he was talking about this as well. So in a way, I will be extending that original argument, which was presented a few weeks ago over here. We know that somewhere around the Miocene, water flow from the Indian Ocean into the Atlantic was cut off. We know that by the middle Miocene, this circulation, which moved from the Indian Ocean into the Atlantic Ocean, was stopped, and it changed into what is similar, or at least more similar to what we have nowadays, with water entering the Atlantic into the Mediterranean, becoming progressively more saline and coming out into the Atlantic as intermediate waters. So we know that this happened at some point in the Miocene. So the big question that I would like to ask myself is this. We have this circulation. The circulation has been going on since the mid-Cretaceous. So at some point, this changes completely. So I'm trying to answer one big question here. And the big question is, once you have this big change in circulation, what effect is it going to have on the climate of the central Mediterranean? In particular, at this point in history, we have to look at the landmass of North Africa. We have to ask ourselves, what would be the effect of rainfall on North Africa? And I will be using Malta. So right here in the central Mediterranean, Malta has been quite a topic of interest for geology, especially for climate changes during the Oligocene and Miocene. There's quite a few papers that have been looking at this from different perspectives. So I will again be making use of the deposits of Malta to try to answer these questions. In particular, there's two sections that I will be looking at. They're quite close to each other on the western coast of the island. So these are marine outcrops, two marine outcrops. The Il Blata section is from the late Oligocene through the early Miocene, whereas the Russell Pellegrini section is a middle Miocene section. I will be going in turn discussing both of these sections. They have quite some similarities, but also their particular differences. So, first of all, the first question that has been answered. So this has been answered back in 2019. So Orbialik and colleagues worked on trying to time the closure of the Mesopotamian Seaway. And the conclusion was as follows. The closure of the Mesopotamian Seaway actually occurred in two steps rather than one, using neodymium isotope as a tracer, comparing data from the Maldives and from Malta. So in Malta, we had already used these two sections. We used Il Blata section, we used Russell Pellegrini section to get neodymium data from the early Miocene and from the middle Miocene. So we have this first important step, which is in the earliest Miocene. So sometime around 20 million years ago, there is a very, very large change of water fluxes from the Indian Ocean into the Mediterranean. And in the middle Miocene, so around the Langin-Seravallian boundary, so this is around a large expansion of the Antarctic ice sheet, we get another one of these steps. It is generally assumed that this step, this final step, is the total and complete disconnection between the Indian Ocean and the Mediterranean. We still think that in between there were intermittent reconnections of waters from the Indian Ocean into the Mediterranean. We've labeled these MSR1 and MSR2 for Mesopotamian Seaway restriction events. So it is here that this is established. So we are now sure that this long-running, low-latitude circulation was cut off. Go back to these two sections in Malta. So MSR1, we identified the neodymium tracer signal at the Il Blata section, MSR2 at the Russell Pellegrini section. I will take the opportunity here to give a very brief overview of the general geology of Malta. It is mostly a carbonate system with shallow water carbonates at the bottom of the section and shallow water carbonates also at the top. In between these two, there is deepening of the carbonate platform, and you get what we call pelagic to hemipelagic units. They've been divided as follows. There's a lower Globigerina limestone member, a middle Globigerina limestone member, upper Globigerina limestone member, and a blue clay formation. So the Il Blata section is in the Globigerina limestone formation. In particular, it is related to a host of phosphorite deposits. The MSR2 is identified in the blue clay formation. particularly around the Serra Valley and GSSP, where the Globigerina limestone shifts to the blue clay. In fact, it's right at the picture I have there behind me. So I will start now taking these sections bit by bit. I will be starting with the Il Blata section first. So why do we go at Il Blata? There's quite a lot of sections in Malta that span the late Oligocene and early Miocene, but it is, to my knowledge, the only section which is mostly developed without, well, there's quite a lot of hiatuses, but compared to other sections, it's not as bad. So we can look at deposits from the Aquitanian and early Burdigalian at Il Blata. It has previously been dated to some extent. So there's quite some interesting work by Carl Felmy using strontium isotopes on the Fomeri section, which is close to Il Blata. There's some work by Baldassini using nanofossils to date this section. So we are quite confident that we know where we are. It is in the central Mediterranean, so it is right in the place where water flow from the Indian Ocean would have passed to get into the Atlantic. There's the phosphorite beds, which are quite well developed here compared to other sections in Malta. And there's also some very interesting chert beds, which, well, they haven't been described much in any previous work. So it's important that we're looking at a site which might be a very, very rare kind of site in the central Mediterranean, a site which hosts this time interval of the Aquitanian and early Burdigalian. So back in 2022, we managed to publish the first paper coming out from the Il Blata section. So we have made use of quite a number of proxies. The thing with Il Blata section is that we did not manage to get those kind of pristine foraminifera that you would want if you're studying these kind of climate studies. But we worked mostly with bulk, and we used also the geology of the site to guide us into what we might be looking at. So in general, the section at Il Blata can be split into two quite distinct geologies. The lower section, which we have termed depositional interval 1, is a carbonate-rich marine deposit. It is very low sedimentation rate. It has these strongly lithified phosphorites, both pebbles and hard grounds. So there's quite a mix of phosphorite bed types. And we know that this section is quite interrupted. There's quite a lot of deepening and shallowing events, as has been described numerous times in previous work. Deposition in interval 2 at Il Blata is quite different. It's clay rich. It is very finely grained. There's high sedimentation rate. It is most likely a fully continuous interval, possibly one small hiatus towards the top. Also contains chert nodules. So the first thing we did was we sort of divided this according to the distinct lithologies of the site. And we produced a new age model. So we produced an age model using strontium isotope ratios. The measurement for the strontium was done in Geneva. And once we place our ages with the height, it becomes very, very clear that there's a very, very large change in sedimentation rate between interval 1 and interval 2. So this is interval 1, the mostly marine limestones with the interspersed phosphorite beds. Interval 2 is different sections of organic rich mudstones, fine-grained limestones, and the bit at the top here is where we have the cherty nodules. So there's quite a big change here, which occurs somewhere around 19.2 MA. So there's a big change in sedimentation rate. We then took some bulk sediment element analysis, and we tried to identify suitable elements that might tell us a thing or two about the environmental situation at Il Blata at the time. So over here we have zirconium aluminium and titanium aluminium, and we have interpreted these proxies to be telling us about the delivery of minerals into the system, whether it is more fluvial related or aeolian related. And using this interpretation, we see that depositional interval 2 is more dominated by river fluxes, whereas interval 1 would be more dominated by wind fluxes, which is probably the kind of, well, it's the kind of environment that dominates the central Mediterranean at the time, nowadays. We also had a look at potassium aluminium to try to have a look at what weathering is dominating our deposits. And if we look at this, we'll see that depositional interval 2 is more prone to chemical weathering, whereas interval 1 is more prone to physical weathering. It's a very interesting record with the silicon titanium, with a large increase in silicon titanium in our bulk sediment towards the chert nodule beds, which are in depositional interval 2, suggestive of a high biogenic silicon production. We also had a look at strontium calcium to act as our sea level control. We put everything on the graph from Bielik with the neodymium isotope tracer, and we see this big change in the neodymium isotope values occurring sort of right where depositional interval 1 changes to depositional interval 2, which also coincides, if we go on the Westerholt-Bentick isotope data curve, coincides with these two very interesting shifts to heavy oxygen isotopes. Quite large shifts. I'm assuming there's quite a big sea level drop at the time. So this is the Oligocene-Miocene transient one, what people call the MI1. These two, I don't think they have any particular name, but they occur right in this change in the neodymium isotope. Also, they occur sort of in the transition where we see the Il Blata section going from the more marine-dominated, wind-dominated fluxes to the more terrestrially dominated, fluvially dominated sediments. So we put all of sort of our data from the Il Blata section onto this diagram. So we have, this is the Westerholt compilation again. So early Miocene is pretty much dominated by these very large shifts in the oxygen isotope record. If we look just after MSR1 event, the record starts to shift towards what one might suggest is a warmer global climate. So this warming trend begins before the climatic optimum over here. There's the Il Blata hiatus between depositional interval 1 and interval 2. There's also a major shark extinction event around the time. And there's also the termination of the phosphorite deposits. So phosphorite deposits occur within interval 1 in the Il Blata section. We don't find any phosphorite deposits in the Il Blata 2. Phosphorites reappear again around the Miocene climatic optimum. So an interesting question here would be, what is happening in the Mediterranean at the time? What is the relationship between what is happening in the Mediterranean and what might be happening globally? So what we are suggesting is that the closure of the Mesopotamian gateway, so we are looking at MSR1, did have a very, very large impact, on global circulation. We are suggesting that as these warm waters are now advecting into the Atlantic rather than going into the Indian Ocean, there's an energizing, an intensification of climate over the Atlantic with an increase of rainfall over Western North Africa. So we are saying that the depositional interval 2 represents this. So we have this site in the Mediterranean that is recording this very large change in climate over North Africa at the time. In Malta, the depositional interval 2 is then followed by, again, we go back to a shift more sort of marine dominated carbonates. So this humid interval we are suggesting here was temporary. It lasted possibly 1 million, 1.2 million years, but possibly not further. At least the influence on Malta was not extending any further. We also think that this surge in rainfall was detrimental to the formation of phosphorites, so the high sedimentation rate would have inhibited phosphorite formation at the time. Now, so I'm going to move now to the Middle Miocene. So before I do that, before we start talking about the Middle Miocene, sort of I'm trying to summarize the MSR events with respect to the depositional sediments in Malta. So I've been talking about the Il Blato deposits here. So depositional interval 1 and interval 2. The change from 1 to 2, there's a big hiatus, but the change coincides with MSR1. MSR2 coincides with a continuous interval in Malta between the Globigerina limestone and the blue clay. I'm mentioning these two sections here. The Marsalforn section is in Gozo. The Russell Pellegrin section is in Malta. So these two sections are considered continuous, and quite a lot of work has been done on these in the past by Badger, by Abels and Maurik in different papers. So there's quite a lot of literature on these sections, which also coincide with the large expansion of the Antarctic ice sheet in the Middle Miocene, and also the carbon maxima 6 in the benthic isotope record. So now I will be shifting my focus over here. So I'll take some time to talk about the Russell Pellegrin section. And again, I'm going to ask myself, why do we go to the Russell Pellegrin section? First of all, this is extremely well dated. This has been investigated many, many times. It hosts a GSSP. It has been astronomically tuned in the past. So this is quite a good place to go if you want sort of your base work done for you. Again, we're in Malta, we're in the central Mediterranean, we're at the place where waters from the Indian Ocean would have been moving on their way into the Atlantic. Again, we are close to North Africa, and it has been suggested in the past. So there's some work by Cedric John from 2003, which has also been discussing this possibility of looking at Malta to identify changes in hydroclimate over North Africa. The neodymium tracer we've mentioned at Il Blato, so the advantages at Il Blato also apply here, that we are looking at a site which is sufficiently removed from volcanic sources. Okay, we are in a marine setting quite far from any volcanic influence. And quite interesting and very, very important is the microfossils at Russell Pellegrin. So again, this isn't something new. This has been done in a number of papers in the past, but the microfossils here are incredibly well preserved. We are looking at a clay-rich lithology which protects the foraminifera. So we have a very, very good geochemical record to access here. I'll look at what has been done in the past. So here we have, next to each other, stabilized dope records from Malta. So these are from a number of different authors, and also different sources. So we have planktic records and benthic records from Mauric 2011. So these are the oxygen isotopes. Over here we have bulk records from Badger and others. And one of the things that will strike you once you start to look at these records is you look at, so TB stands for transition bed. The transition bed between the Globigerina limestone and the blue clay formation is where we identify the Mi3b oxygen isotope excursion. It's where we host the GSSP for the Langin Cerevellian. Again, it's the thing behind me in the background. Once we are beyond that, so we move from the limestones into the blue clay, if we look at the planktic oxygen isotope record, we start to notice this very, very large variability in the oxygen isotope record. We do see some of that over here in the clay-rich interval, was originally named by Cedric John. So we see there's a bit of a clay-rich interval in the Globigerina limestone, but then the whole blue clay record tends to have this quite large variability in the planktic record. We do not see that in the benthic record. It is not so clear in the bulk record. So we made use of previously sampled materials. So we made use of the samples from Marcus Badger and some of the samples from Anja Mauric from previous papers. And well, we went and had a look at the foraminifera again. So this is very different. The laboratory approach here is very, very different from the Il Blata approach. In Il Blata, it was mostly powdering rocks and measuring XRF, measuring carbonate content. Here we picked individual foraminifera. We selected planktic and benthic species. We picked them individually. We cleaned them with acetone, cleaned them in the clean lab, and put everything through the mass spectrometer in order to measure stable isotopes again. So we have a new stable isotope record and a trace metal record to complement previous trace metal records from the Russell Pellegrini section. So the microfossils chosen, so we have Elobatos, Trilobius, and Ovigerina species. The SEM images demonstrate the suitability of these microfossils for geochemical analysis. So we are looking at very well preserved specimens, which give us confidence, which give us a lot of confidence in our interpretation of the geochemical records. So what are the records that we have? So I start with the stabilized dope records. So I'm not going to talk much about the carbon isotopes this time around, but I'm focusing on the oxygen isotopes. So we have the planktic record and the benthic record. Both records show this gradual shift to higher values of the oxygen 18. But if we focus on the planktic record, again, we see this high variability in the oxygen isotope record of the planktic foraminifera. Again, this confirms what we had already seen in the records of Mauric. We then took a magnesium calcium record, again, from both planktic and benthic. We screened for aluminium calcium because this is clay-rich lithology, and we wanted to make sure we are eliminating that our cleaning protocol was enough to eliminate aluminium contamination. So in the end, we screened to values, we eliminated values for the aluminium calcium that had values higher than 100 micromoles per mole, and we ended up with these two graphs. So we have a magnesium calcium for the planktic record and the magnesium calcium for the benthic record. And we made use of these to obtain temperature records for surface waters and bottom waters. And the Russell-Pellegrin section has been estimated, this paper by Belanca in 2002, estimated around 500 to 600 meters water depth. So we have this temperature gradient of surface waters and bottom waters. So our aim was to identify changes in surface waters at the time. So what we did was we use our temperature records and our stabilized slope records in order to separate from both the bottom water and the surface water signals. We wanted to separate the temperature signal. So bottom waters, we end up with an ice volume signal, which is the blue graph over here. Whereas in surface waters, we end up with both an ice volume, but also a precipitation evaporation signal, which is what we want to look at. So we decided to subtract the two records, and we ended up with the green graph, which represents the precipitation evaporation signal in surface waters, which we are interpreting as a salinity proxy. So if we look at the earlier part of our record, these parts over here represent significant freshening of surface waters at the time, significant freshening at surface waters at the time. And what we did then, we applied a different equations to get a similar graph, but in practical salinity units. So if we look at this part, we are talking of shifts going down as far as 34 and 35. So central Mediterranean these days can go up to around 38 PSUs. The Atlantic at a similar latitude to Malta at the time was around, these days would be around 37 PSUs. So we are looking at this interval right after MSR2, right after the expansion of the Antarctic ice sheet in the Middle Miocene, to have a significant freshening of surface waters at the time. We look again at these graphs. So this is significant freshening, but we also have these two intervals of quite significant increase in salinity in the surface. If I go back here, well, it suggests that this can go up to 40 or around 41 practical salinity units. It's quite interesting that when we look at these real high salinity intervals, they also coincide with a decrease in ice volume as interpreted in our benthic records. So we are thinking that the waxing and waning of the Antarctic ice sheet, its influence on the intertropical convergence zone would have also influenced climatic belts over North Africa. So these humid intervals might have been shifted further south. And when that happened, the reduction in flux of fresh waters into the Mediterranean would have made the Mediterranean go into real high salinities. Well, this is quite high, even higher than what we would experience these days in the central Mediterranean. So even though the Mediterranean was now getting really restricted, we still find this close coupling with the global climate as driven by the Antarctic ice sheet. So we try to put everything into one graph here. So this is the lithology of the Russell-Pellegrin. So this is the Globigerina limestone here, transition bed, and the blue clay. The expansion of the Antarctic ice sheet, so excursion MI3b, can be seen in this change in the Westerhold benthic isotope data here, whereas our age model allows us to place MSR2 just a bit after that. So this allows us to exclude a causative mechanism by MSR2 on the expansion of the Antarctic ice sheet. there could have been some feedbacks from MSR2 onto the climate system. I will talk about these in a moment. So over here, we have sort of a bit of everything. We have the original Mauric isotope data with the very large shifts in the oxygen isotope just after the Mi3b excursion. We have our surface temperature records, and we have our salinity proxies over here. And there's the neodymium isotope record to tie up the MSR2 event. What could have been the sources? So if we look at this diagram from Hounslow 2017, there's quite a lot of work in Libya and Tunisia, in the Sirte Basin, Fezzan Basin, Adamis Basin. So there's quite a lot of possibilities. So a lot of the work in this Hounslow paper stems from the early Miocene all the way through the middle Miocene, suggesting intermittent existence of very large lakes in the region. So I don't think it's unreasonable to suggest that there would have been outflows into the Mediterranean from these areas. And what we're looking at in Malta is the edge of a delta system, and we are right at that edge, and we are sort of looking at what is happening in North Africa in our pelagic to hemipelagic section. We can look at some models. So there's this model by De La Vara 2016. It has been discussed in Bialik 2019, and we made some small changes to it. So if we go to the latest Oligocene and the early Miocene, so you get waters from the Indian Ocean at the surface moving into the Atlantic, and you get bottom waters moving over the Sardinia block and Sicily and Malta sill. Possibly this also helps in the formation of the phosphorite beds by bringing nutrients from deeper waters. So this could explain the formation of these phosphorites. It's quite interesting. These phosphorites seem to be at low latitudes. There's phosphorites in California at the time, Florida, there's phosphorites in Malta and Sicily. So there's quite an interesting question to be made as to these Oligocene to early Miocene phosphorites, possibly why they were there. And we are suggesting they stopped. One possible reason is the closure of this Mesopotamian gateway. So if I look at the MSR1, MSR1 would have been this situation. The Mesopotamian seaway is either completely closed or very, very shallow, as Bialik suggests. So waters from the Atlantic enter the Mediterranean and go back into the Atlantic as more saline, more warm, and this energizes the Atlantic, and you get the rainfall patterns as we are suggesting over the Mediterranean. After this, so in the middle Miocene, throughout the climatic optimum, the higher global sea level would have reopened this gateway, maybe to a smaller extent than what it was in the late Oligocene. It could explain why we might get some phosphorites again in Malta at the time. Possibly after the mid-Miocene expansion of the Antarctic ice sheet, the combination of tectonics and lowering of sea level would have shut off this gateway completely. So, to close off, so we have evidence from Malta that shows that we have these two humid phases over the central Mediterranean related to MSR1 and MSR2. The MSR1 and MSR2 are mediated by a combination of tectonics and global Eustachy. It is quite interesting that on a global climate level, MSR1 and MSR2 occur against two different backdrops. So MSR1, you have the early Miocene expansions of the Antarctic ice sheet. There's quite a few of them. Towards this cold arid phase, we get MSR1. after MSR1, the global climate starts to warm up again. Whereas MSR2 occurs right after the permanent expansion of the Antarctic ice sheet. So we have these two events. They are both driving humidity over North Africa. We might be looking at a proto-monsoon over Western North Africa in MSR1 and possibly a more robust monsoon in MSR2, but the global climate backdrop is different in each case. We are saying that these are driven by this more energetic waters entering the Atlantic. We still think there is close coupling between the expansion and contraction of the Antarctic ice sheet and climate over the Mediterranean. We also suggest that MSR2 may have acted as a positive feedback. There's some models which suggest that these waters which are outflowing in the Atlantic, also the cutting off of waters from the Mediterranean into the Indian Ocean, may have further helped in the thermal isolation of Antarctica, intensifying the Antarctic circumpolar current. Okay, so some sponsors there, the Open University Geological Society, there's my local sponsor, Endeavour Scholarships, and sponsors from Cardiff University, which have allowed me to do these studies. Thank you very much for your attention, and I will be happy to discuss any matters and questions that arise.
Thank you, Ray. So let me see if there are any questions. I wanted to ask a little question. So you were talking about there being fluvial influence within the sediments in the bladder section. So weren't the rocks you were looking at, they're mostly carbonate though, aren't they?
So I should have put some pictures of the bladder section. I think I vomited some of that. There are carbonates in what I call depositional interval 1, but then in depositional interval 2, there's quite a drop in the carbonate content. There's quite a lot of muds and clays, and we also have siliceous deposits towards the end. So there is.
I remember that. Yeah. So are these coming from Africa? Presumably it's from Africa.
Well, it's a good question, and I've been asked this before. Some people asked me, why aren't they coming from Sicily? I think if we look at the paleogeography at the time, I don't think there's enough landmass in Italy to have. I mean, if you look at Malta on a map and you measure the distances to Tunisia or to the Gulf of Sirte, it's quite far. So in order for us to be looking at these pelagic and hemipelagic units, we are here at the edge of a deltaic system. So it must have been quite an extensive deltaic system.
And also in the RIP section, right, you have that blue clay. Again, that's sort of like a delta. You were thinking that's like a distal delta deposit.
But the blue clays, I think there's less than 30% carbonate in that. I know there's numbers, and it tends to change a lot. I mean, there's these darker and lighter bands throughout. They've been astronomically tuned, so there's quite shifts in the amount of clay content that you get. They've been tied to precession cycles, so that's why we talk about monsoonal kind of variable climate.
So you had mentioned neodymium isotopes, but those were for the water, right? People haven't done neodymium isotopes on this clay, have they? Okay.
The neodymium isotopes comes from bulk. So in Malta we did bulk rock. Those were measured by Martin Frank in Germany.
Right.
So yes, they're from the bulk. Okay. And yes, so we took samples from the limestone and from the clay. We sort of.
Yeah, I just wondered if the neodymium helps you to confirm that the deltas are coming from Africa.
No, we haven't looked at that.
Okay, thank you.
Thank you.
does anyone else want to ask a question? Jerry, why don't you go ahead?
You're muted.
He is muted.
I am muted. Hey, Ray, thank you for the talk. I enjoyed that.
Thank you.
Your chert nodules. So where's the silica coming from? I mean, there's not much silica in the Mediterranean today, is there? Not deposition of.
No, well, I think again, it's coming from the continent. There's quite a lot of chert nodules all over Tunisia, Algeria. I think there's a couple of papers coming from Tunisia. I think even Morocco. So if you map it out, there's real large amounts of chert deposits in these areas all around the early Miocene. I think one of the big problems is the age models with these. So having a good correlation to say this is all happening around what I call MSR2 is not the easiest task on earth. But I do think there could have been like a silica bloom. There's quite a lot of happening. There's changes in circulation. There's warming. So this is very different. We are now entering a warm, humid phase. So it is possible. It is possible. There's a big change into the kind of productivity that is happening in surface waters at the time. So changing from carbonate to more like silica dominated. It's not a long interval. I think it's less than 1 million years. But
I mean, to me, that's the interesting thing. I'm guessing it must have come from siliceous microfossils, the silica for the chert. But
yeah,
almost ubiquitously, we think of those as usually colder waters where we're forming, for example, if we go to the Eastern Equatorial Pacific, we get the silica band along the cold waters of the upwelling. And so here you're going into a warm interval and you get the chert. And I was thinking, well, that's sort of interesting. So it seems backwards intuitively, but I mean, clearly the data is the data. Yeah. So
we don't really know. There are some few. I think there's paper by Muttoni and Kent, if I'm not mistaken, that have looked at like the chert throughout the Oligocene and the Miocene, and we are not sure exactly what the chert is representing. So in Malta, it's it's a very small section, very small area. Yeah. But again, if you look at, I think it's called the Babouche Formation. So it's huge. It spans like most of the Western North African coast. And I think there's also deposits in Sicily as well. But again, we are looking at these land-based sections, which through time, they have been given different age models. They've been given wrong age models. They've been erroneously mapped. And, it's not easy to correlate all these things.
Oh, thanks. I mean, that sounds really interesting. Maybe I should come over to Malta and look at them. Thank you very much. I really enjoyed that.
Thank you.
So,
there's
Tara, got a question. You want to ask your question?
Sure. Yeah. So kind of leaping off of Peter's previous question, because he actually asked my question about the neodymium, because I was curious about what that was measured on. Because I noticed it correlated a little bit with some of where your phosphate sections were, but that's another question entirely. But I guess I was curious with your wind and fluvial fluxes, is that if you noticed any cyclicity in those patterns, or if just the resolution is there at the moment. So
the Ilblata section, so when I look at these two sections, they're really, really different. If you look at Russell Pellegrini, you can do anything. The fossils are great. The resolution is amazing. I think the original Mauric paper, if I remember correctly, they resolved that to, I think, definitely 9,000 year intervals, but I think even more. I think there's a lot of data in Utrecht, and I worked on some of that, and not a lot of that has been published. They've been amassing data from Russell Pellegrini, and so with Russell Pellegrini, we are happy. We've also done some spectral analysis, and we know there's quite a big precessional influence going on. Ilblata is a different story. We couldn't isolate microfossils. I wasted a lot of time trying to do that, so we went bulk. I think in some of it there is potential. There is some potential to try to do the section again. So I just took samples every, I think, 30 or 50 centimeters. it is, it's not a very big section. It's not a very big section, but I think there is potential to go through the muds, work on the bulk, possibly the nanofossils, and like do that in like a real high resolution. And that will be, I think what is interesting is we are looking like the Burdigalian. So if you allow me, am I still sharing?
Yes.
So if I go back. So we are looking at this bit in history, so between about 19.2 and 18.5. And I don't think there's much out there in literature which really looks at this bit. Particularly in the Mediterranean, there's a lot of hiatuses. So I think it's worth a try if there's time and money and people to work on this, to sort of go back in the field and like try to take samples every few centimeters. But again, one has to work on bulk. So I think one could try something like even basic calcium carbonate measurement as a start.
Yeah, it's great section, clearly. So there's all sorts of things you can do with it. Yeah.
But again, microfossils, I mean, nanos possibly, yes, it's possibly. Baldassini in Italy had done the nanos to age this section. But not foraminifera. I mean, there are foraminifera, they're quite small. They're not everywhere, and well, it will be quite a lot of time to pick them out and see if they're suitable for any geochemistry. Honestly, I don't know if they are.
Okay, thanks.
Thank you.
Thank you. Are there any other questions? If not, then I think we should thank Ray for his presentation. And thank him also that this is actually the last monsoon seminar for the time being. And we will see if we come back in the future. It depends on whether people want to talk. But at the moment, we were going to take a summer break anyway, and there's no plan to return in the autumn. So for the time being, at least, this is the end of the monsoon seminars. Thank you all for coming. And of course, Ray's talk will be online in the usual way on YouTube, and we'll send out the link to Zoom as well. But thank you so much for coming, and I wish you the best of a summer or winter if you live in the southern hemisphere. And that's all, folks. Thank you very much.
Thank you.